Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello all you pre-calculus students out there. My name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is another video in sequences and series to prep you for calculus. You should have watched my videos on sequences and summation notation. In that video series, I talked about the definition of a sequence. We did some problems with sequences. We talked about recursively defined sequences and partial sums of a sequence. We talked about summation notation and the properties of summation notation. All of that's going to be kind of critical for our discussion here. And in this video, we're going to focus in on arithmetic sequences specifically. It's a very special kind of sequence. So there are actually really two major types of sequences that we deal with in mathematics commonly, but there's probably quite a few more than that. But the most common are going to be arithmetic sequences and another one yet to be stated. So what is an arithmetic sequence? An arithmetic sequence is a sequence of the form A being your first term. So maybe I should write this down below. So A1 would be A, A2 would be A plus D, A sub 3 would be A plus 2 of those D's, and A sub 4 would be A plus 3 of those D's, and so on and so forth down the line. This should hopefully look like a linear function to you, and that is because it really actually is a linear function. And we'll investigate that in a little bit to kind of clarify that statement. But let's go ahead and define every little piece here. D, which is in almost all these terms here, D is called the common difference of the arithmetic sequence. It's basically what you step by every single time you increase to the next term. For example, if you had an arithmetic sequence defined, by the following, then every single time, so let's look at what A sub 1 is. If you plug 1 in, you'll have 3 times 1 minus 1, which is 0, plus 1. So A sub 1 is 1. A sub 2, though, if you plug 2 into this, you'll get 3 times 2 minus 1, or 3, plus 1, which is 4. If you plug 3 in to find out what A sub 3 is, you'll have 3 times 3 minus 1, which is 2. So 3 times 2 is 6, plus 1 is 7. Now notice, as we continue down here, I'm just going to write one more in, that the difference between these, we are just adding 3 every single time. That is the common difference between them. And that's why we call it the common difference. Also, this kind of justifies my statement that these act like linear functions. That is, arithmetic sequences very much act like linear functions. If you can see this, it is written like almost like a 3x plus 1. It's not exactly 3x plus 1, but it's kind of like a 3x plus 1. Obviously, the function 3x plus 1 has a domain of all real numbers, whereas the sequence 3 times the quantity n minus 1 plus 1 only has the natural numbers as its domain, or possibly the whole numbers, maybe some negative integers, but generally speaking, we just let n start at 1. But if you take a look at the values for this, f of 1 would be 4, f of 2 would be, 6, 7, and f of 3 would be 10. Notice those numbers actually appear over here, right? So it very much looks like the behavior of an arithmetic function mimics that of a linear function. Instead of calling our 3 a slope, we're just calling our 3 a common difference. But really, you can kind of think of it this way. If somebody hands you an arithmetic sequence and they tell you the common difference is 3, you can think, oh, that means the slope is 3. So common differences are very much like slopes. And in this regard, technically, you could have learned arithmetic sequences right after you learned linear functions. It is very much, they go hand in hand. Linear functions and arithmetic sequences, that is. All right, let's see what else we have to tackle here. This whole video is just getting us used to arithmetic sequences, and there's a lot in here, but it all revolves pretty much around this format right here, talking about common differences, recognizing that each step of the way you're just adding that common difference to get to the next term in the sequence. And then we're going to talk about how you can really quickly develop an equation an equation or a pattern for an arithmetic sequence. And that's really going to happen right here. Theorem: the nth term of an arithmetic sequence is given by the following. A sub n is equal to a plus n minus 1 times the quantity, a plus the quantity n minus 1 times d. That is the nth term of the arithmetic sequence, with the first term being a and the common difference being d. The proof of this actually just relies upon the definition of an arithmetic sequence. So let's go ahead and write down the definition of the arithmetic sequence. So we'll say let a sub n be the arithmetic sequence with common difference d and starting term a. When I say starting term, that really means the initial term of the sequence. Normally we call that a sub 1, but let's just call it a for this conversation. Then by definition, the terms of the sequence are a sub 1, which is equal to a sub 2, which is just d plus that original value, a sub 3, which is another d plus that last value, and a sub 4 is just another d plus, again, that last value. It's almost recursively defined, if you will. So if you take a look at that, this means that the nth term in the sequence is a plus, well, if you look at the pattern, 3, 2, 4, 3, that tells us that this is just going to be n minus 1. Whatever n is, this will be n minus 1, d. And honestly, that's it. You're done, because that's what we want to prove. So the equation for that sequence is a sub n is equal to a plus n minus 1 in quantity d. Now, before I exit this page, I do want to kind of draw your attention to a difference between this, the arithmetic sequence formula there, and the equation of a line. Equations of lines look like this: y equals mx plus b. And yet I'm telling you that the equation of an arithmetic sequence is very much like that. It is n minus 1 d plus a. Notice how I rearranged that there. So let's see why there's an n minus 1. Why is that an n minus 1 instead of some other value? And by the way, actually, really, if I'm going to write it just like y equals mx plus b, it should be that this d is there and this is the n minus 1, because d is playing the role of the slope. It's the common difference. If you had a slope to your linear equation, I don't know if anybody's ever told you this, but if you have, let's say, a line y equals 3x plus 1, let's just say, that means that every time you take a step forward by 1, you rise by 3. Step forward by 1, rise by 3. That's a rise over run situation. So the linear, or I should say slope addition property, tells us that for each increase of 1 in input, the y value will change by m. Again, if you had y equals 3x plus 1, well, if you increase the input, the x value, by 1, the y value will change by 3 because it's rise over run. So the run was 1, the rise is 3 because that's the slope. So therefore, it does confirm that. And if you look over here, actually, maybe I should look here. For each increase of 1 in input, from the number 1 to the number 2, our output is increasing by d. So it's a very similar concept. The output is always increasing by the same number every step of the way. So this very much has like a slope addition property as well. And in fact, I'll go ahead and write that right here. For each step of 1 in the index, the output changes by d. So you can see there's a strong similarity there. Also, note with a linear function, if you were to let x equal 0, so y of 0 is equal to, you would get b. So b is called the initial value, right? That's what we're used to from our good old Algebra 1 days. Initial value is just b. That's what we call the y-intercept. Well, there's no such thing as a y-intercept for a arithmetic sequence, because normally the first value of n you're plugging in is 1. So you're not going to plug in n equals 0. The first value you're going to plug in is 1. However, if that's the case, if you're plugging in 1, which is our initial value, you will get a, right? Because if you plug in 1, you get 1 minus 1 there. So you get a. A is, again, what we would consider to be the initial value. So everything's lining up very nicely to showcase that, yes, arithmetic sequences are just like linear functions. The strong difference between them is this. One has an x and one has an n minus 1. Like, what's up? Why is that an n minus 1? Why isn't it an n? And the reason why it's not just an n is because we have to subtract 1, because our sequence doesn't start with an index of 0. It starts with an index of 1. And if we happen to know that a sub 1 was supposed to be a, then I need to turn this very first term off when I plug in n equals 1. And the only way to turn that term off with an n equals 1 is to say that that term is something times n minus 1. And then plugging in 1 for n will turn that off. So that's the only reason why that n minus 1 is there, is because we basically are shifting our linear function over to start at 1. Remember your transformations of functions? So if I had y equals 3x plus, let's just say 1, it would look like that, right? In this case, what I'm essentially doing is saying, I need, if I want my first value to be 1, the first output to be 1, I need to shift that function over to the right 1 unit to the right. And that means that it's, instead of 3x plus 1, it's 3 times x minus 1 plus 1. You're shifting things over to the right. If that's lost on you, that's okay. Just note that it is critical that you remember the equation of an arithmetic sequence is always basically slope times n minus 1 plus initial value. Whew, that was a lot to go through, right? So now we get to go into examples. For the given arithmetic sequence, and you know it's arithmetic, by the way, just by looking at the form. It's a number times n minus 1 plus a number. Doesn't have to be, by the way, times n minus 1. It can be manipulated in such a way that it doesn't look like it's arithmetic, but essentially anytime that you have a sequence of the form like this, 7/3 n plus 2, let's just say, or maybe it's minus 2 actually. Now in this case right here, it could be that you're handed something like this. This is still an arithmetic sequence, because you could see it looks like a linear function. So don't be fooled if the n minus 1 is not there. You could force it to be there. You could say, well, how do I write this in that arithmetic sequence form that I was told it should be in? Well, one way you can do is you can just say, well, here's what it is originally written as. Let me go ahead and just subtract 1. Of course, that subtraction of 1 wasn't originally there, so you're going to have to offset it by adding that 1 times 7/3, because you're technically subtracting 1 times 7/3 by putting that -1 there. And when you do that, you get 7/3 times the quantity n minus 1, and then you have -6/3 plus 7/3, so plus 1/3. Whoops, plus 1/3. So you, as long as it looks linear in form, it can be made into an arithmetic sequence in standard arithmetic sequence form. That's what I would probably call this, standard arithmetic sequence form. Anyhow, all right, and I can't even remember if that's exactly what I was talking about. I got a phone call partway in between there, so if I sounded like I jumped topic a little bit, it was because I came back from a 15-minute phone call. Now, the first part of this, find the first 5 terms, is not going to be a killer issue, right? A sub 1 is going to be 1/3, because if you plug in 1, you get 1/3. A sub 2, let's see, that's 7/3 plus 1/3, or 8/3. And by the way, there's no reason for me to actually look at this anymore, because I know the common difference is 7/3. And so I know that every time I go to the next output, I'm just adding 7/3 to the previous output. So now I could just use that trick there. Let me add 7/3 to 8/3, and I will get 15/3, which is 5. And so that was just gotten from adding 7/3 to the previous 8/3. And then to go to a sub 4, I'll just add another 7/3 here. Well, that is 15/3 plus 7/3 is 22/3. So let me write that down, 22/3. And then finally, a sub 5, add yet another 7/3, that'll be 29/3. And that again is just because we're adding yet another 7/3. So really writing out the first 5 terms is not a big deal with an arithmetic sequence. Stating the common difference is also not a big deal. The common difference d is equal to 7/3, because that's the slope. Remember, common difference is basically the slope. And finally, graph the terms. Well, this will be more educational than anything else. Let's go ahead and graph down a horizontal line, and I'll plot some numbers on here. N equals 1, n equals 2, n equals 3, and then 4, and then 5. And of course, there is technically some type of vertical axis way over here. Call that the y-axis, even though you don't really need to call it that. And this is the n-axis. And let's see, when we plugged in 1, we got an output of 1/3. So what I'm going to do is scale my y-axis intelligently here. I plotted in where I think the height of 1/3 should be, just because I want it to be there. And then notice my scale is just everything's 7/3 away from each other. So 1/3 to 8/3, that's supposed to be a 3, but it doesn't look like it. And then 8/3 to 15, which is, 15/3, which is 5. Sorry about that. And then 15/3 to 22/3 is another 7/3 of a step. And then 22/3 to 29/3, again, another 7/3 in step. And if I were to plot these values, I would say, okay, well, when I plugged in 1, I got out of 1/3. When I plugged in 2, I got out an 8/3. When I plugged in 3, I got out of 15/3. When I plugged in 4, I got out of 22/3. And when I plugged in 5, I got out of 29/3. And you can easily see that if I were to connect those points, which I'm not going to, because they're supposed to be distinct. There's not, sequences are not continuous functions. But if you were to connect them, I'm just going to magically do it and then erase, they would all exist on the same line because they're linear in form. Okay. It's a linear relationship, I should say. There you go. So that's how you do that full problem with a lot more explanation behind the scenes. And now we're starting to head into some oddball questions, some questions that might not quite fit the pattern of, hey, here's an arithmetic sequence, find the first 5 terms and all that stuff. Instead, somebody says, I have an initial value of square root of 2 and a common difference of root 5. Find the nth term and the 100th term of the arithmetic sequence with those 2 conditions, that the initial value is root 2 and the common difference is root 5. Well, all they're really asking me to do is build the arithmetic equation, right? A sub n, find the nth term. Remember, it's always of the form slope times n minus 1 plus basically initial value. So a sub n, here is root 5 times n minus 1 plus the initial value of root 2. That is the nth term. And then they're asking, well, could you please find the 100th term? Yeah, don't be silly. I totally can do that. A sub 100 is just going to be 99 times root 5 plus root 2. There's not much else I could do there. That's the value of the 100th term. With that last example, I wish there was more I could say about it, but there really isn't. That last example is as good as it gets with that last example. But don't worry, we have a lot more examples to go here. So let's determine if this following sequence of values is arithmetic. And if it is, let's find the common difference. Well, remember, to be arithmetic, you have to be able to add the same number over and over to get to the following term in line. That is, let me go ahead and write this down. We added 2 to get from A1 to A2. We added 2 to the y value, or the output, I should say. But when we went from A2 to A3, we didn't add 2, we added 4. So immediately I happen to know this is not arithmetic. And that's all I need to say with this. Notice how quick some of these problems are. Is this arithmetic or not? This technically is something called geometric, which is the most popular style of sequence out there. But we learned that in another set of videos, but it's a really nice one. Geometric is when you're constantly multiplying by the same number. Notice we multiplied by 2 to get from A1 to A2, and we multiplied by 2 again to get from A2 to A3, and then again by 2 to get from A3 to A4. But don't worry, that's not the purview of this video, so let's not worry about it, right? So here's the same question. Is this arithmetic? If it is, find the common difference. I will again just write down the values. Nothing big. Should have used black ink, but that's not that big of a deal. ... This is A1, this is A2, and this is A3. And why not? This is A4. Now let's see. To get from A1 to A2, what do we add? 1.7? I should probably double check my mathematics. Yes, we did. If you add another 1.7 to 4.3, you'll get to 6. That does work. And we add another 1.7 to get to 7.7 from 6. So yep, this looks to be arithmetic. So I'm going to say arithmetic. And to answer their question, I'm going to say with common difference of a 1.7. Again, they didn't ask me to write down the formula, although I totally could. The formula here is just going to be 1.7 times n minus 1 plus the initial value, which is 2.6. Totally could do that. They didn't ask me to, but there you have it. Now, I really like this one. It's kind of written out of order. It should have been our second question here, but it's okay. Let's just go ahead and approach it now. Find the first 5 terms of that sequence and determine if it's arithmetic. Now, you and I both know, you and I being you as a group of citizens and I as a single person, know that this is going to be arithmetic because it's linear. If you were to rewrite this, it is 1/5 n plus 4. That is like a linear function. I totally know this is going to be arithmetic. The problem is it's not n minus 1 there. It's just n. But you could force it to be an n minus 1 if you want, or you should actually, by doing this. Oh, it's like 1/5 times n and then plus 4. And we'd all nod our heads and say, yes, it sure is. And then you come in and you say, but wait, I need this to be a minus 1 in here. But that blue ink was not there to begin with. So I have to offset that blue ink with some blue ink on the outside. Well, that blue ink is not a -1, actually. It's a -1/5. So I need to offset the -1/5 that I included by including a +1/5. And now I have a really nice form for this, now I know, arithmetic sequence, which is 1/5 times the quantity n-1, and then 4 plus 1/5 is 21/5. There we go. But again, they want me to write out the first 5 terms. We could totally do that if we want to. I don't know if I really want to. I'm kind of bored with that. I did it anyway, just because you probably wanted it there. And notice, all I did was start with an initial value of 21/5, and that is just from this nice clean version over here. And then I just added 1/5 each time. 21/5, 22/5, 23/5, 24/5, and then 25/5, which is 5. So this is a very fast way to do this style of problem, and it doesn't really honestly take too long to do it, so that's pretty good. We do need to state the common difference, so I'm just going to point at, now I'll just write it down. There we go. The common difference is 1/5, and everything else we've answered, right? State the common difference. We have the nth term. That's this piece right here. So we are totally done with this problem. Again, not trying to speed my way through it, but there's really not a lot to do with arithmetic sequences. They're just like linear functions, which is super nice. You feel like this is awesome. You should feel like, oh yes, like pre-calculus, this is not so hard. So let's see if this one challenges us anymore. Determine the common difference. So right when they say that, determine the common difference, I know that they're giving me an arithmetic sequence. And in fact, they actually state it at the end of the given arithmetic sequence. So determine the common difference, state the 5th term, the next term in line, state the 100th term, and then the nth term. Let's see. I will go ahead and write down those values. And they're telling us it is arithmetic. That means that the difference between these two is constant, just like the difference, all the differences between any two consecutive terms in the series is going to be constant. So all I need to do is a single subtraction. I can subtract any A1 from A2, or A2 from A3, or A3 from A4. I could do any of those. I'm just going to go ahead and off to the side say, what is A2 minus A1? So that I can find out what did I have to add to A1 to get to A2. A2 is 5/3. A1 is 7/6. That's 10/6 minus 7/6, which is 3/6, which is 1/2. And let's double check that. Did I really add a half here? 7/6 plus 3/6 is, let's see, 7/6, 3/6 is 10/6, which reduces to 5/3. That's correct. And then 5/3 plus a half. Okay. Well, 5/3 is the same thing as 10/6. Add another 3/6 and you get the 13/6. Oh, that does work. Okay. I don't really need to check the last one. Now that I know that it's all linking up, that's perfect. So our common difference is 1/2. Well, then I can easily find the 5th term, which is what they're asking for next, because it's just 1/2 away from the 4th term. And the 4th term was 16/6. Add 3/6 to 16/6, and you're at 19/6. And so we know the 5th term, a sub 5, is 19/6. Now here's the deal with this. I include this kind of backwards because I want you to know how to read a problem. Often we read parts of a problem, myself included, by the way. I'll read parts of a problem and I'll just start answering. I'll just say, oh, determine common difference. Let me go ahead and start determining the common difference. And then I say, oh, there's the 5th term. Let me go ahead and do that next. The reality here is I should read the entire problem and figure out what's probably the smartest thing to do first. So determine the common difference. then the 5th term, the 100th term, and the nth term of the given arithmetic sequence. The common difference, actually, that should be the first thing I find. But once I find that, I actually can quickly form the nth term. I can easily say that the nth term is going to be that common difference, which we said was 1/2, times n minus 1, plus the very first term in our sequence, which is 7/6. Now that I have that, I technically could just have used that to find out what a sub 5 is. I didn't, but I could have. But I'm totally going to use this to find out what a sub 100 is, to find the 100th term. That's going to be, let's see, 99 over 2 plus 7 over 6. Well, now that's going to require a little bit of mathematics on my part. 3 times 99 is nearly 300. It's 297. Plus 7 is 304 sixths. Somebody's going to yell at me if that's wrong. But I literally just checked. It's okay. And this reduces down to 152 thirds. So really, we've again quickly answered the entire set of questions here within this one question pretty easily. So again, arithmetic sequences are not too terrible. Where does it terrible when does it get terrible? That's what you should be asking. When does it get terrible? Well, to be honest with you, even here, as we graduate through these problems, even this is not going to be terrible as long as you remember that arithmetic sequences operate almost identically to linear functions. The 12th term of an arithmetic sequence is 32. The 5th term is 18. Find the 20th term. Now, given this question, I'm actually just going to find the nth term. What is the pattern? Like, what is the overall arithmetic sequence? It's just much easier to do that. So here's how I suggest doing it. Treat it as if it were a function. I know when n is equal to 12, a sub 12 is going to be 32. That's 1 point they've given me. And then I also know when n is equal to 5, the a sub 5 is going to be 18. I'm just stealing that information from these pieces right here. And if it is true, and it is, that arithmetic sequences act just like linear functions, then I just want to find the slope between these 2 points, and that will be my common difference. Again, let me say that. I want to find the slope between these 2 points right here, and that will be my common difference. So setting up the slope formula, y2 minus y1 over x2 minus x1, you get, what is that, 32, that's 14 over 7, that's 2. Great, my common difference is 2, which tells me I know that my function, or I should say my arithmetic sequence, looks like this. 2 times n minus 1 plus some initial value of a. Gosh, I wish I had enough information to find that value of a. Lo and behold, I do. I could choose either of these points to plug in. So I know, for example, when n is 5, my output should be 18. And then I'll have my formula for my arithmetic sequence identically. 2 times 5 minus 1 is 8. Subtract 8 from both sides, and you get that the initial value is 10. And therefore, I happen to know our arithmetic sequence. Oops, that's seg. Let's do sequence. Our arithmetic sequence is given by a sub n is equal to 2 times the quantity n minus 1 plus 10. And now if you ask me for the 20th term, fine. If you ask me for the 100 trillionth term, I'll do that too. So a sub 20 is equal to 2 times 19 plus 10. That's 38 plus 10, or 48. There you go. It's like you get a full review of linear equations when you're dealing with arithmetic sequences. And now we're to the last question in this specific video, which is just all about arithmetic sequences. We will deal with partial sums of them in the next video. That's a whole different beast. But for now, this is a really cool question. If you have an arithmetic sequence defined by 1, 47, 7, and so on and so forth, the question is, which term is 88? In other words, what is the end value? What's a sub what is equal to 88? Well, the fact that a sub 1 is equal to 1, and a sub 2 is equal to 4, and a sub 3 is equal to 7 tells me that the common difference is 3. So D is equal to 3. Notice I'm constantly just setting up the equation. All right. And so this will be a sub n is equal to 3 times n minus 1 plus the initial value, which is 1. And I want to know, when is this output equal to 88? So let's go ahead and do that. 88 is equal to 3 times n minus 1 plus 1. Let's find out when that occurs. Subtract 1 from both sides, divide both sides by 3, and what do we get? N minus 1. 87 divided by 3 is 29. And add 1. I'll just do that. Add 1 to both sides, you get 30. Perfect. That is beautiful. So, to answer the question, which term of the arithmetic sequence is 88? Well, it's the 30th term of that arithmetic sequence. All right. So that concludes kind of an introduction to arithmetic sequences. The next video will focus significantly on partial sums of arithmetic sequences.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Names for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.